The solar system is about to feel a whole lot smaller. We stand on the brink of an era where the word distant loses its meaning for worlds like Mars and Jupiter. This shift hinges on one field, advanced propulsion, and the revolutionary engines being designed right now. By the end of this journey, you will understand 15 specific systems that could turn our cosmic neighborhood into a collection of nearby destinations. We will explore how spacecraft might ride beams of light, harness the power of artificial stars, or even manipulate the fabric of space itself. What does it truly mean for humanity when a journey across the solar system is no longer a lifetime commitment, but a manageable voyage? The ultimate engine would run on pure destruction. Our journey begins not with a gentle push, but with an instantaneous flash of energy so profound it defines the upper limit of physics. This is the Antimatter Rocket. In its simplest form, the concept is breathtakingly direct. You take a particle of matter and you introduce it to its perfect opposite, its mirror image with opposite charge, known as antimatter. When they meet, they do not simply react or burn. They annihilate each other in a total conversion of mass into energy, following Einstein's famous equation. Every single gram of fuel is transformed into a staggering burst of power. To grasp the scale, consider this. The chemical engines that lifted astronauts to the moon convert less than 1% of their fuel's mass into usable thrust. A nuclear fission reactor might reach about 1/10 of 1%. An antimatter annihilation converts 100%. The difference is not incremental, it is monumental. It is the difference between a campfire and the heart of a star. With such efficiency, a spacecraft could achieve a significant fraction of light speed, making a trip to a nearby star system a voyage of decades rather than millennia. A probe could reach the outer planets in months, not years. The raw power offered is so immense it redefines what is possible within a human lifetime. Yet this power comes with a price of almost equal magnitude. Antimatter does not exist naturally in any usable quantity in our universe. Every single atom of it must be painstakingly manufactured in particle accelerators, a process that is currently so energy-intensive and slow that producing a single gram could take a civilization's entire industrial output for millennia. And once you have this priceless fuel, you must store it. Antimatter cannot touch any container made of normal matter, or it will instantly annihilate. The solution involves suspending charged antimatter particles in perfect vacuum chambers using incredibly powerful magnetic fields, a feat of engineering that has only been achieved with microscopic quantities for fleeting moments. So the Antimatter Rocket stands as a paradox. It is simultaneously the most powerful propulsion system we can conceive of with known physics, and one of the most difficult to ever realize. It represents a pinnacle, a benchmark against which all other advanced concepts are measured. If the Antimatter Rocket is the ultimate expression of raw power within the universe's rules, then what happens when we start looking for ways to bend those rules themselves? That raw, annihilating power of antimatter is a distant dream, but our next system brings a star's fire within closer reach. We are talking about the Fusion Rocket. Think of it not as an explosion, but as a sustained, controlled burn, a miniature sun you carry with you for the journey. This engine would work by fusing light atoms, like forms of hydrogen, together. When these atoms fuse, they release a staggering amount of energy, the same process that powers every star in the cosmos. Unlike the brief, violent bursts of our chemical rockets, a fusion drive could provide a gentle, continuous thrust for months or even years. This is the key to high-speed travel within our solar system. Imagine accelerating halfway to your destination, then flipping the ship around and decelerating for the second half, all under a steady, manageable push. A trip to Mars could shrink to weeks. A voyage to the icy moons of Jupiter might take months instead of years. The solar system suddenly becomes a network of highways, not isolated outposts. The ambition goes even further. Pioneering studies like Project Daedalus, conducted by the British Interplanetary Society in the 1970s, outlined a robotic probe powered by inertial confinement fusion. Their theoretical design suggested a vessel that could reach a nearby star like Barnard's star within a single human lifetime. While the engineering challenges are immense, primarily in achieving and containing a self-sustaining fusion reaction in a compact, space-worthy format, the physics is sound. This is what makes the fusion rocket so compelling. It does not require rewriting the laws of the universe like an antimatter engine might. It requires us to master a force we already know exists on a stellar scale. It represents a plausible bridge, a tangible stepping stone from where we are now to where we dream of going. It is the technology that could truly begin the era of interstellar humanity. Yet, even as we learn to bottle starlight, another concept asks a more radical question. What if the fastest way to travel isn't to move through space, but to move space itself? That idea of moving space itself is a frontier for another day, because we already have a technology that defies our instincts about thrust, working silently in the vacuum right now. It produces a force so gentle you could barely feel it in your hand, a push weaker than the weight of a single sheet of paper. Yet this whisper is reshaping our solar system. This is the ion thruster. Forget the violent fire and thunder of a chemical rocket. An ion drive is a study in elegant efficiency. It works by taking a heavy, inert gas like xenon and stripping an electron from its atoms, creating a soup of positively charged ions. These ions are then focused and accelerated out of the engine by a powerful electric field, shooting backward at speeds exceeding 100,000 miles per hour. The reaction pushes the spacecraft forward with that faint, persistent whisper. The key is not the strength of the push, but its incredible stamina. A chemical rocket burns all its fuel in a few furious minutes, achieving high thrust but then coasting for the remainder of its journey. An ion thruster is the opposite. It can fire continuously for months or even years, slowly, steadily adding speed. Over those long stretches, the velocity builds to numbers chemical rockets can only dream of, all while using a fraction of the fuel. We are not just theorizing, this is proven operational science. NASA's Dawn spacecraft, which launched in 2007, was a silent pioneer of this method. Fitted with 3 ion thrusters, it embarked on a marathon voyage. It used its gentle, blue-glowing jets to spiral its way from Earth's orbit to the asteroid Vesta. Enter orbit, study it, then leave orbit, and journey onto the dwarf planet Ceres, entering orbit there as well. This was an unprecedented feat, a single spacecraft orbiting 2 different celestial bodies, made possible only by the incredible fuel efficiency of ion propulsion. The patience required is profound. An ion thruster spacecraft takes months just to spiral out of Earth's gravity well, a trip a chemical rocket makes in hours. But once in the deep ocean of space, it becomes a true marathon runner, accelerating long after its chemical cousins have gone silent. This makes it the perfect engine for the solar system's long-haul routes. Unmanned cargo ships supplying future bases on Mars could use ion drives, carrying massive payloads on slow but steady trajectories, conserving precious fuel for generations of missions. Deep space probes heading to the distant ice giants, Uranus and Neptune, could rely on these persistent whispers to carry them across the billions of miles. It redefines the relationship between power and time, proving that sometimes the most powerful force is not a sudden explosion, but unwavering, patient persistence. And if we can master patience to such a degree, what happens when we combine that patience with the raw power of our own sun? Patience is a virtue, But what if the solar system offered us a free ride? A spacecraft equipped with an ion drive still carries every ounce of its own fuel. But there is a resource already flowing past us at incredible speeds, a river of energy we could learn to sail. This is the plasma sail, often called a mag sail. Forget canvas and ropes. Picture instead a spacecraft deploying a colossal loop of superconducting wire, perhaps hundreds of kilometers across. When an electric current runs through this loop, it generates an immense magnetic field, a vast, invisible bubble that billows out around the vessel. This magnetic bubble is the sail. Its purpose is to catch the solar wind, the constant stream of charged particles, protons and electrons, that erupts from the sun and races outward through the solar system. As these high-speed particles strike the magnetic field, they push against it, transferring a tiny bit of their momentum to the spacecraft. The thrust is incredibly gentle, even more so than an ion drive, but it is utterly free and continuous. The spacecraft carries no propellant to be exhausted. It simply deploys its magnetic net and lets the sun do the work. The true elegance of this concept, however, lies in its dual nature. For a mission to another star, the greatest challenge is not just getting up to speed, it is slowing down upon arrival. A conventional rocket would need to carry enough fuel to accelerate halfway and then decelerate for the second half, doubling the already impossible fuel requirements. The magsail offers a brilliant solution. As the craft approaches its destination star, it would reorient its magnetic sail. Now, instead of catching the solar wind from our sun, it would use the incoming stellar wind and radiation pressure from the target star itself as a brake. This elegant symmetry turns the entire journey into a single, graceful maneuver. The spacecraft uses the push from its home star to leave and the gentle pressure from a distant sun to arrive. It transforms the space between stars from an empty, forbidding gulf into a navigable medium, a cosmic ocean with currents we can finally harness. It is a concept that marries profound capability with a kind of beautiful simplicity, using the universe's own resources to explore it. Yet, if we can sail on the solar wind, what might we achieve if we could build a harbor and create our own perfect artificial wind? A harbor for spacecraft does not need to be a physical place. It can be a principle, a method of turning raw, chaotic power into a directed and reliable stream. This brings us to a system that is neither a whisper nor a sail, but a controlled roar from a bygone era of ambition. The nuclear thermal rocket stands as a testament to a path we nearly took. Its principle is brilliantly straightforward. Instead of burning chemical fuel, you use a compact nuclear fission reactor as your heat source. You pump a lightweight propellant, typically liquid hydrogen, through the white-hot core of that reactor. In an instant, the super-cold liquid is flash-heated into an immensely energetic gas, blasting out of a nozzle to create thrust. The key advantage is efficiency. Chemical rockets are limited by the energy stored in the molecular bonds of their fuel. A nuclear thermal rocket is limited only by the heat tolerance of its materials. This allows it to achieve roughly twice the efficiency or specific impulse of the best chemical engines. For a crewed mission to Mars, this is transformative. It could slash transit times from 9 months down to 4 or 5, dramatically reducing the crew's exposure to deep space radiation and the psychological strain of confinement. This is not speculative futurism. We built and tested these engines under projects like NERVA in the United States during the 1960s. Engineers successfully ground-tested full-scale reactors that ran for hours at thrust levels perfect for launching spacecraft from Earth orbit toward other planets. The technology worked, and it worked well. It represented a bridge that was nearly crossed, a future where interplanetary travel became a matter of months, not years. Its shelving was not due to failure, but to a shift in political priorities and funding away from deep space ambitions. Today, that bridge is being inspected once more. Modern programs are revisiting the nuclear thermal rocket with advanced materials and computer modeling, aiming to create safer, more robust versions for the coming era of lunar and Martian exploration. It represents a pragmatic, powerful step, a way to shrink our planetary neighborhood using a fire we already know how to light. It asks us a compelling question. If we had the tools for faster travel half a century ago, what other dormant ideas from our past might hold the key to our future among the stars? That dormant fire of nuclear engines offers immense power, yet it still requires us to carry the very fuel we burn. But what if we could leave the fuel behind entirely and voyage on a beam of pure energy sent from home? The answer is not a sail for the solar wind, but one for sunlight itself. This is the solar sail. Think of light not just as something to see by, but as something with physical substance. Every photon, every particle of light carries a tiny amount of momentum. When light reflects off a surface, it gives that surface a minuscule push. For us on Earth, this force is imperceptible, lost in the crush of gravity and atmosphere. But in the frictionless void of space, with nothing to oppose it, that tiny push can add up. A solar sail spacecraft is designed to catch this gentle rain of photons. It deploys vast, incredibly thin sheets of reflective material, often aluminized plastic thinner than a human hair, stretched over a framework that can be kilometers across. It looks less like a ship and more like a shimmering cosmic butterfly. Sunlight falls upon this gigantic mirror and pushes it ever so slightly onward. The acceleration is agonizingly slow at first, far less than the gentle whisper of an ion drive, but here is the magic. Unlike any rocket that eventually runs dry, the sun never stops shining. The push is constant, hour after hour, day after day, year after year. With no fuel to exhaust, the spacecraft can accelerate continuously. Over months, it builds a respectable speed. Over years, it can achieve velocities that would be the envy of conventional probes, all without a single drop of onboard propellant. This is not just a beautiful theory. In 2010, the Japanese space agency JAXA launched a mission called Icaros. It successfully deployed a square solar sail about 46 feet across, and using only the pressure of sunlight, it navigated a course past Venus, proving the technology works in deep space. It was a silent, elegant ballet of physics, a demonstration that we can indeed sail on sunbeams. For robotic explorers, this changes everything. A solar sail-powered probe could embark on a grand tour of the solar system, using the subtle pressure of light to swing past planets, adjust its orbit, and journey to the outermost reaches. Its mission duration limited only by the durability of its materials, not its fuel tank. It is the ultimate expression of sustainable space travel, a craft that truly lives off the land, or rather, the light of the cosmos. It turns our sun from a distant heat source into a perpetual engine. But if we can sail on the light from our sun, what if we could build an even brighter sun, one we could aim? But sunlight is a gentle, diffuse breeze perfect for a patient voyage. For a sprint to the stars, we would need a hurricane of focused energy. This is the promise of beam-powered propulsion, a concept that reimagines the very idea of a launch. Forget carrying a power plant on board. Instead, picture a spacecraft that is little more than a sail and a payload, a cosmic kite. Its engine remains firmly on the ground or in orbit as a colossal array of lasers or microwave transmitters. At the moment of launch, this array focuses a tightly concentrated beam of energy directly onto the spacecraft's sail. The pressure from this artificial beam is millions of times more intense than sunlight. It pushes the craft forward not with a whisper, but with a sudden, sustained shove of pure light. Because the vehicle carries no fuel and only a lightweight reflective structure, it can achieve accelerations and final speeds that are simply impossible for any traditional rocket. The mathematics are staggering. A small, wafer-thin probe fitted with a meter-scale sail could, under the relentless push of a powerful Earth-based laser, reach speeds of 20% or more of light speed within mere minutes. At that velocity, a flyby mission to our nearest stellar neighbor, Proxima Centauri, would take just over 20 years. While that is still a profound journey, it transforms an interstellar voyage from a multi-generational epic into a project that could see its own results within a single human career. The true elegance is in the division of labor. The monstrously complex, energy-hungry, and stationary power source stays where we can maintain and upgrade it on Earth or in a stable orbit. The spacecraft itself becomes a simple, durable, and mass-producible vessel. We could launch fleets of them, each one a different instrument package, each one pushed to incredible speeds by the same ground-based engine. It turns exploration into a scalable endeavor. Yet, this beautiful concept is not without its own profound challenges. Aiming a laser beam across light years with perfect precision is a feat of optics beyond our current mastery. The sail material must be near perfectly reflective to avoid being vaporized by the immense energy, and it must be incredibly thin and strong to be pushed to such extremes. And perhaps most poetically, the spacecraft can only be pushed. It cannot use the beam to slow down at its destination, as the beam from Earth would take years to catch up to it again. It is a one-way ticket to a high-speed flyby, a breathtaking glimpse of another world in a blinding instant. It is a system built for discovery, not for arrival. But if we can push a craft to such speeds with an external beam, what other external forces in the universe might we learn to ride? A flyby is a breathtaking glimpse, but a true starship must carry its own fire. It must become a creature of the deep, feeding on the galaxy as it travels. This is the audacious promise of the Fusion Ramjet, often called the Buzzard Ramjet after the physicist who first conceived it. Picture a vessel not with a fuel tank but with a mouth. Stretching before it is a vast electromagnetic funnel, a net of magnetic fields thousands of kilometers wide. As the ship moves at a significant fraction of light speed, this immense net sweeps through the thin soup of the interstellar medium, the stray hydrogen atoms that drift between the stars. It funnels and compresses this collected hydrogen, directing it into the heart of the ship where a fusion reactor waits. There, the interstellar hydrogen becomes the fuel, fused into helium to release energy and provide thrust. The beautiful, almost poetic logic is that the faster the ship goes, the more hydrogen it scoops per second, potentially increasing its fuel supply and acceleration. In theory, this creates a virtuous cycle, a self-feeding engine that could allow for continuous acceleration across the vast distances between stars, never needing to carry a drop of fuel from home. The cosmos itself becomes both the ocean and the fuel depot. It is the ultimate vision of a self-sufficient starship, one that lives off the land of deep space. But the scale of this vision is almost incomprehensible. Creating a magnetic scoop large enough to collect meaningful amounts of the incredibly diffuse interstellar hydrogen is a feat of engineering that dwarfs anything humanity has ever attempted. The fields would need to be stable across distances larger than planets, and the fusion reactor would need to ignite and burn a thin, incoming stream of fuel with perfect reliability for decades. Furthermore, later calculations suggested a troubling complication. Within our region of the galaxy, much of the interstellar hydrogen is not in the form of lone atoms ideal for fusion, but as charged particles or tied up in molecules, which might be far harder to collect and use efficiently. So the Buzzard Ramjet stands as a magnificent thought experiment, a blueprint for a kind of cosmic freedom that may be just out of reach with our current understanding. It challenges us to think not about what we can carry, but about what the universe can provide. And if we cannot always rely on the galaxy to offer us fuel, perhaps we must look for a way to bring a far more potent piece of the universe with us. The concept of a ship feeding on the galaxy is a grand vision of self-sufficiency, but it still accepts the vast, empty distances of space as a given. What if the ultimate solution is not to travel across space, but to cheat, to bring your destination to you? This brings us to the single most radical idea in theoretical propulsion, the Alcubierre warp drive. Forget engines and thrust. Picture a spacecraft sitting motionless inside a bubble of normal spacetime. Now imagine that this bubble is not passive. The fabric of the universe in front of the bubble is being pulled tightly together, compressed. Simultaneously, the spacetime behind the bubble is being stretched and expanded. The bubble itself, with the ship inside, is then carried forward on this wave of distorted spacetime. It is not moving through space faster than light. Instead, space itself is moving, carrying the bubble along like a surfer on a wave. Within the bubble, the laws of physics, including Einstein's cosmic speed limit, remain perfectly intact. The crew would feel no acceleration, experience no time dilation, and could theoretically travel at speeds many times faster than light without ever breaking a single rule of relativity. The implications are staggering. A trip to Proxima Centauri, which would take tens of thousands of years with today's technology, could become a journey of weeks or even days. The entire Milky Way galaxy, with its hundreds of billions of stars, would transform from an unreachable expanse into a navigable archipelago. Our solar system would shrink from a sprawling frontier to a local neighborhood, a single stop on an endless galactic tour. The mathematics behind this idea, first published by physicist Miguel Alcubierre in 1994, are sound within the framework of general relativity. The equations show it is possible, but mathematics and reality are separated by a chasm filled with what we call exotic matter. To create the warp bubble, you would need to generate a ring of material with what is known as negative energy density around your ship. This is not antimatter, which has positive energy. This is something truly bizarre, a substance that would exhibit negative gravity, repelling rather than attracting. While certain quantum effects suggest negative energy densities can exist in microscopic amounts, like in the Casimir effect, we have no evidence such a material can exist in the macroscopic, stable quantities required to warp a starship-sized volume of space. The energy requirements are also almost comically vast, initially calculated to be equivalent to the mass energy of Jupiter. Later refinements have suggested ways to reduce that requirement, but it remains far beyond any conceivable technology. So the Alcubierre drive exists in a fascinating limbo. It is not science fiction, as it emerges from our best equations of gravity. But it is not yet science, as it depends on materials and energies we cannot fathom creating. It represents the outermost boundary of our imagination, a signpost pointing toward a future where the very geometry of the universe becomes a highway. It forces us to ask a humbling question. Are the vast distances between stars a fundamental barrier? Or are they merely an engineering problem waiting for a civilization clever enough to solve it? And if manipulating spacetime itself is the pinnacle of theoretical travel, what other profound manipulations of physics might we one day achieve? The warp drive asks us to bend the universe, but there is an even more profound frontier. What if the engine was the universe itself? Deep within the equations of quantum mechanics lies a ghost, a whisper of infinite potential hiding in what we call empty space. According to the theory, a perfect vacuum is not truly empty. It is a turbulent sea of quantum fluctuations where virtual particles flicker into and out of existence in a continuous dance. This background hum of the cosmos is known as zero-point energy, and it suggests that space itself contains a staggering amount of latent power. The vacuum energy thruster is the ultimate expression of a wild idea. Could we build an engine that pushes against this quantum foam? Could a spacecraft extract thrust from nothing more than the fabric of reality? The concept, sometimes called an M-drive or a quantum vacuum plasma thruster in various experimental forms, proposes a device that would convert this zero-point energy directly into motion without expelling any propellant whatsoever. It would be the holy grail, a propulsion system that needs no fuel tank, no reaction mass, just an understanding of the universe so deep we could tap into its underlying vibrations. Imagine a spacecraft that never runs out of fuel, that can accelerate continuously as long as its quantum engine is running, powered by the endless churn of empty space. It defies our classical intuition about motion, where every action requires an equal and opposite reaction. If you are pushing against the quantum vacuum itself, what pushes back? The very idea challenges centuries of conserved momentum, standing at the razor's edge between groundbreaking discovery and physical impossibility. While a handful of controversial laboratory experiments have reported minute, unexplained thrust effects, the results remain deeply contentious within the scientific community. Most physicists attribute the tiny observed forces to measurement error or thermal effects, not a revolution in physics. The energy densities required to meaningfully interact with the quantum vacuum are astronomically beyond our current capabilities, and the theoretical framework for such an engine remains speculative at best. Yet its enduring allure is undeniable. It represents the final frontier of propulsion thought, a system that does not just use the universe's resources like sunlight or hydrogen, but attempts to use the universe's very substance as its foundation. It is a reminder that our understanding of reality is incomplete, and that the next great leap may not come from building a bigger rocket, but from listening more closely to the silent hum of the cosmos. The hum of the quantum vacuum is a whisper from the edge of physics, but our next system roared with the unmistakable thunder of its time. It was born not from subtle equations, but from the raw, terrifying power of the atomic age. This is nuclear pulse propulsion, the infamous Project Orion. Its principle was shockingly direct, a kind of cosmic cannonball run. The spacecraft would eject a small atomic bomb out the back. Moments later, the bomb would detonate. The resulting plasma fireball would slam into a gigantic, curved pusher plate at the rear of the vessel, protected by a layer of ablative oil. The shockwave would push the entire craft forward before another bomb was ejected, and the cycle repeated, like a machine gun firing pulses of pure nuclear energy. The proposed rate was staggering, one bomb every few seconds, a continuous drumbeat of detonations propelling a city-sized starship across the void. The scale was beyond anything before or since. Early designs envisioned vessels weighing thousands of tons, more akin to floating naval battleships than traditional spacecraft, capable of carrying entire colonies to Saturn or massive fleets on interstellar voyages. The performance metrics were equally breathtaking. While a chemical rocket might reach Mars in months, an Orion ship could theoretically make the journey in weeks. A mission to the outer planets could be a matter of a single year, not a decade. It was brute force engineering on a monumental scale, a declaration that the solar system could be conquered not with finesse, but with overwhelming power. Yet, this immense capability was inextricably linked to its profound cost. The political and environmental realities of the Cold War era, along with growing global treaties banning nuclear explosions in space, ultimately grounded Project Orion before any metal was cut. The vision of hundreds or thousands of atomic detonations in Earth's magnetosphere, even for peaceful exploration, presented risks the world was unwilling to take. So Orion remains a powerful historical what-if, a testament to a parallel path not taken. It demonstrates with chilling clarity that the technology to dramatically shrink the solar system existed in principle over half a century ago, wielded with tools of terrifying potency. It forces a profound question about progress, one that echoes into our present. Must our greatest leaps forward always be born from our most destructive discoveries, or can we find a gentler, cleaner path to the same stars? Orion's atomic thunder represents a brute force approach, but our next system is a whisper of elegant simplicity. It requires no fuel, no reactor, and no sail. Instead, it turns a planet's own magnetic personality into a silent engine. This is the electrodynamic tether. Picture a satellite in orbit around Earth. From it spools out a long, thin wire, perhaps tens of kilometers in length. This is not a simple cable, but a sophisticated, conductive tether. Now, recall that our planet is wrapped in an immense, invisible magnetic field, the same force that guides a compass needle. As this tether cuts through that magnetic field while orbiting at thousands of miles per hour, something remarkable happens. The motion through the field naturally induces an electrical current to flow along the length of the wire. This is basic electromagnetic induction, the same principle that allows a generator to create electricity. But here, the satellite becomes the generator. By deliberately controlling this current, engineers can create a force. When an electric current flows through a wire within a magnetic field, it experiences what is called the Lorentz force, a push perpendicular to both the current and the field. By switching the direction of the current, you can switch the direction of the push. This means a satellite could use its tether to give itself a gentle, continuous thrust to boost itself into a higher orbit, or to lower itself for re-entry, all without firing a single thruster or expelling a drop of propellant. The implications are profound for managing our growing orbital infrastructure. Aging satellites that have run out of fuel, which would otherwise become dangerous, drifting debris, could deploy a tether to slowly lower their orbit and burn up safely in the atmosphere. New satellites could be launched to lower, cheaper orbits and then use a tether to patiently climb to their operational altitude, saving massive amounts of fuel and cost. It is a form of cosmic judo, using the planet's own inherent forces to achieve motion. The tether transforms the magnetic field from a passive backdrop into an active transportation network, a set of invisible rails upon which our machines can glide. While the forces involved are modest, they are constant and free, making them perfect for the long-term, meticulous work of orbital housekeeping and positioning. It is a technology that speaks to a more sustainable future in space, one where we learn to work with our environment rather than simply overpowering it. And if we can turn a magnetic field into a gentle engine for satellites, what other subtle forces in the cosmos might we one day learn to harness for far grander voyages? The silent, magnetic highways of electrodynamic tethers are a marvel of subtlety, but sometimes a journey demands more than a gentle nudge. Enter the realm where fire becomes a tool, not an explosion. This is the Helicon Thruster, a device that conjures propulsion from a storm of superheated gas. It belongs to the family of electric propulsion, like the ion drive, but it trades a bit of that system's extreme efficiency for a far more muscular push. Instead of patiently accelerating individual ions, a Helicon Thruster creates a dense, roaring torrent of plasma. The process begins with a neutral gas like argon or xenon flowing into a chamber. Here, radio waves are pumped in, their frequency tuned to resonate with the gas atoms. This resonance efficiently strips electrons away, creating a soup of charged particles, a plasma. But the radio waves do more than just create this plasma. They continue to pump energy into it, heating it to tremendous temperatures. This hot, dense plasma is then guided and accelerated out of the nozzle by magnetic fields, producing a bright, continuous exhaust plume. The result is a thruster with a thrust density significantly higher than its ion drive cousins. Where an ion engine provides the persistent whisper needed for a decade-long cargo haul, a Helicon Thruster offers a stronger, steadier breath capable of more substantial maneuvers. This makes it a compelling candidate for the next step, crewed missions within the Earth-Moon system or to Mars. Astronauts cannot afford voyages measured only in fuel efficiency. They need transit times shortened for their safety and sanity. A spacecraft equipped with an array of Helicon thrusters could provide that crucial balance, a continuous acceleration strong enough to cut months off a journey while still sipping fuel compared to a chemical rocket. It represents an evolution, a maturation of electric propulsion from a delicate, specialized tool into a robust workhorse. It is the bridge between the patient, whispering promise of ion drives and the immediate, fiery demands of human exploration, proving that the path to the stars may be lit not by a single brilliant flash, but by the sustained, controlled burn of a smarter kind of fire. Fire can propel us, but sometimes the most powerful force is a well-timed nudge from a world itself. This brings us to a method that is not an engine, but a masterclass in celestial navigation, a technique that has already taken our robotic ambassadors to the very edge of our influence. It is gravity assist, the art of using a planet's own motion as a slingshot. Think of a spacecraft approaching a planet from behind, relative to the planet's orbit around the Sun. As it swings close, the planet's immense gravity pulls it in, whipping it around in a curved path and flinging it back out into space. The key is the transfer of momentum. The spacecraft steals a tiny, almost imperceptible fraction of the planet's own orbital energy. To the planet, a behemoth like Jupiter, this loss is utterly insignificant. But to the spacecraft, this stolen energy is transformative. It exits the encounter moving significantly faster than it arrived, gaining speed without firing a single thruster. It is the ultimate free ride. This is not a theoretical trick. It is the silent engine behind our greatest voyages of discovery. The twin Voyager probes, launched in 1977, executed a grand tour of the outer solar system by threading a series of these gravity assists. Jupiter gave them a push toward Saturn, which flung one toward Uranus and the other toward Neptune, accelerating them to speeds that eventually allowed them to escape the Sun's gravity entirely. Without these celestial billiard shots, their journeys would have taken decades longer or been outright impossible with the fuel they carried. The Cassini mission to Saturn performed an even more intricate dance, using multiple flybys of Venus, Earth, and Jupiter to build up the momentum needed to reach the ringed planet. Each gravity assist was a carefully calculated pivot, a cosmic pirouette that turned the solar system into a network of gravitational stepping stones. Today, this ancient art is being refined by a modern tool, artificial intelligence. Plotting a trajectory that uses multiple planetary flybys is a problem of staggering complexity, a multi-body puzzle where every slight adjustment changes the entire future path. Advanced algorithms can now explore millions of potential routes, finding sequences and close approaches that human planners might never conceive, squeezing every last ounce of free velocity from a fleeting planetary alignment. It is trajectory optimization raised to an art form. This technique does not shrink space itself, but it dramatically shrinks the time and fuel required to cross it. It turns the solar system from a collection of isolated destinations into an interconnected web, where every world becomes both a destination and a potential launch pad for the next great leap. It is the ultimate cosmic hack, a reminder that sometimes the most profound propulsion system is not something we build, but something we learn to borrow from the universe's own grand orbital dance. And if we can master the dance of planets to travel faster, what other silent rhythms of the cosmos might we one day learn to follow? The silent rhythms of gravity assist are a cosmic gift, but they are bound to the slow, majestic orbits of the planets. For true freedom, we must learn to conduct our own symphony of light. This brings us to our final frontier in propulsion, a system that turns a beam of photons into a finely tuned, resonant engine. It is the photonic laser thruster. Picture a spacecraft equipped not just with a sail, but with a high-quality mirror. Now, imagine a powerful, Earth-based laser aimed with exquisite precision at that distant mirror. The light strikes the mirror, and instead of simply pushing once and being lost to the void, a significant portion of it is reflected perfectly back toward its source. Here is where the magic happens. That returning beam is caught by the laser array on Earth, which then re-amplifies the light and sends it right back to the spacecraft mirror. The photons are trapped in a resonant cavity, bouncing back and forth between the station and the ship, each trip adding another tiny push. This photonic recycling is a brilliant amplification trick. A single photon can make multiple round trips, imparting its momentum to the spacecraft over and over again before it is finally lost. This means that for a given amount of laser power beamed from Earth, the thrust on the spacecraft can be multiplied by a factor of hundreds or even thousands. It transforms a powerful push into a sustained, immense force. The implications are profound. Where a standard laser sail might only be able to push a tiny, wafer-thin probe, a photonic laser thruster could, in theory, propel much more substantial payloads. A manned vehicle or a large cargo ship carrying the building blocks of a future colony could be accelerated to high speeds using this resonant beam. It offers a level of control and efficiency that pure beam pushing lacks, as the closed loop allows for precise adjustments to the spacecraft's trajectory by tweaking the laser's aim. It is the ultimate refinement of sailing on light, turning a diffuse breeze into a focused, recyclable hurricane. The engineering hurdles are, of course, staggering. Maintaining a perfectly aligned laser beam over interplanetary distances through the turbulence of Earth's atmosphere and the solar wind is a monumental challenge in optics and tracking. The spacecraft's mirror would need to be near perfect and remain flawlessly oriented. Yet, the promise is a propulsion system of unparalleled elegance, one that uses the universe's most fundamental particle not as a one-time push, but as a reusable tool, crafting a bridge of pure energy across the solar system. It suggests a future where our journeys are not measured by the fuel we carry, but by the conversations of light we learn to sustain. From the patient whisper of an ion drive to the cosmic shortcut of a warp bubble, these 15 visions are more than just engines. They are a spectrum of possibility, stretching from the tools we are testing today to the dreams that stretch the fabric of physics tomorrow. Each one, whether a solar sail catching sunlight or a theoretical drive harvesting quantum foam, represents a different answer to the same profound human question. How do we reach beyond our horizon? The journey to shrink the solar system is not a single path, but a branching tree of ingenuity. It demands the stubborn pragmatism of an engineer and the boundless curiosity of a poet, for the solutions lie as much in advanced materials and precise mathematics as they do in our courage to imagine the universe as a place we belong. So we turn the question to you. In this gallery of future voyages, which key feels most compelling to you? Is it the near-term promise of a nuclear thermal rocket shortening a trip to Mars, or the distant dream of surfing a wave of compressed spacetime? Let that conversation continue below. Thank you for exploring these frontiers of motion with us. If you want to dive deeper into the technologies shaping tomorrow, subscribe and join us for the next discovery. The cosmos is vast, but our curiosity is boundless. Let's keep exploring together.